Hi, welcome to this video on phenols or phenols, however you want to pronounce it. I'm going to start off by apologizing that it's been so long since I posted something. When I was originally looking at who was viewing, it didn't look like there were very many views, so I didn't think they were being used, and then checked back in last week and there's obviously a few of you out there who are watching and hopefully are finding these videos useful. So I'll keep posting. And I'll start posting a little bit quicker than what I have been doing. So today it's going to be on phenols. Like I said in the last video, I'm going to try and make it a quick one. Just go through some of the properties, some of the reactions that you need to know, and then an exam question. And then in the future videos, I'm going to do a video on polymers because they can be a little bit tricky. And that should wrap up organic chemistry unless any of you have a particular question that you want me to go through. So if that's the case, you can leave a comment or message me, and I'm happy to do a video on any specific question that you might have. Then I'm going to go into redox, so I'll do some videos on redox reactions, so particularly your electrochemical cells or your electropotentials, and your redox titrations. In those I'll include the net ionic equations. Then going on to equilibrium, particularly buffers, because those can be tricky. And then enthalpy videos, so lattice, enthalpy, enthalpy of solution, enthalpy of hydration. So I'm going to focus more on the enthalpies that you would have seen in year 13 instead of year 12, because the year 12 kind of just carries over into year 13. Alright, so on to today, phenols. So one thing you need to always keep in the back of your mind is that phenols are a weak acid, okay? Meaning they will dissociate, but dissociate very, very weakly, okay? And because they do dissociate, I'm talking about that part of it there, they will react with sodium hydroxide and metals. Okay, so for these, you just have to remember back to your acid-base reactions. So if we have our phenol reacting with NaOH, it's that H that will come off and end up binding to that OH there to make your H2O. Okay, and you make a salt, because in acid-base reactions, you get a salt and water. So we have our O- ion and your Na+ ion. Okay, so there's your salt and your water. Same thing if our phenol is reacting with a metal, say lithium, because lithium is fairly reactive. Now in this case, acid reacting with metal, you end up with your hydrogen gas and your salt. Okay, with these reactions, always remember to be balancing them. So we have 2 hydrogens being produced, only 1 there, so we need a 2 there, 2 there. Oh, sorry, that shouldn't have been sodium, that should have been lithium. Okay. And then 2 there to make that balanced. Alright, so hopefully that is okay, because it is just going back to acid-base reactions or acid-metal reactions. So keep that in mind. That could pop up as a synthesis question. Okay. Now the next little thing with reactions is remembering that this is an electron donating group. So I talked about that in the last video, meaning that you get electrons donated to that benzene pi system, which makes it a 2, 4, 6 directing group. So in the next reactions that we see, we're going to be looking at other groups being added onto either the 2, 4, or 6 position. So remember, the OH, the phenol, is always the first position. So we have that being our second carbon, 3, 4, 5, 6. Okay. So if we look at the nitration, okay, so adding a nitro group, benzene ring, the OH. Now we are adding dilute HNO3. So this is going to add our nitro group, and it being a 2,4,6 directing, you can get your NO2, add it there, or let's squish that together a little bit. So in the second position or the fourth position. Okay, so if we look at the names of these, this would be 2-nitrophenol, and this would be your 4-nitrophenol. Okay, so that is adding our nitro group. Now, unlike with a benzene ring, trying to add a nitro group to your benzene ring, the fact that this is electron donating, it means that we're activating that benzene ring, which is why we can use dilute nitric acid. We don't need concentrated nitric acid. This happens a lot easier with the phenyl group on there than it would if it was just a benzene ring. Okay, so that's that one. We can also look at adding halogen, so halogenation. Okay, so 3Br2, so we're looking at adding 3 bromines, so 2, 4, 6 positions. And again, this is an activated benzene ring because of that OH group. So you don't need any sort of halogen carrier. This happens spontaneously. So it's actually a good way of testing for a phenol versus a benzene, because in this case you'll have your bromine water, which is orange, which will go colorless because it's being added on to that benzene ring. You will, also end up having HBr produced. Okay, HBr is colorless. Okay, so you're going from orange to colorless, so a good test for phenols there. Similar to how you would test for alkenes, right? An alkene, you get your bromine that reacts across your double bond, so it goes colorless. All right, so hopefully we are okay with that reaction as well. So the last little one, before we do an exam question, is the reaction with an acyl chloride, where you're going to make a ester in the end. Okay. So we have our phenol group, so an acyl chloride, something like, make sure those bonds are clearly drawn. All right, so in this case, this is where we are going to have that hydrogen there end up binding with that chlorine to make HCl. which means we can form a bond between this oxygen and that carbon. So our organic product be that oxygen. I'm going to draw that carbon and then draw everything that's bound to it. Okay, so naming this ester, it's the same as you would name any other ester, where the name of the alcohol comes first and then the ending of the name is well, the carboxylic acid. In this sense, it's not a carboxylic acid, it's an acyl chloride, but it's where that carbon is double bonded to that oxygen. So the alcohol was our phenol, so we have phenol, and then 2 carbons there, so eth and no 8. All right, so that's all I have for your phenol reactions. So if I erase all this and we take a look at an exam question, I am going to be referring to that mind map that I've been talking about in the last video. So if you haven't drawn your mind map yet for this video, take a moment now and start writing it out. Okay, see if you're at the stage where it's memorized. Okay, hopefully you're getting close to memorizing it at this point. Your exam's in June. So I would hope that most of the reactions you have, there might be a few that you just have to take another glance at and be like, oh yeah, I forgot about that one. But hopefully we're starting to get to the point where you have the mind map memorized. And if you're not using a mind map, that's fine. But whatever strategy you are using, make sure that you're at the point where you know these reactions. Okay, it makes it a lot easier trying to tackle a synthesis question if you could remember the reactions. And like I said in the first video, if you have the mind map memorized and you write it out first thing when the exam starts, then it's easy just to refer to it. Okay, so this is our exam question. Oh, let me just erase this so it's not coming through. So a nice little flow chart again. So complete the flow chart by showing the missing organic structures in the boxes and stating the reagents on the dotted line. All right, so we want to go from our functional group to begin with, phenol, and somehow we're adding an amine in the end. So first off, we haven't really talked about how to add an amine to a phenol. Okay, so we have to think of that intermediate. How can we go from our phenol to having an amine? So if we just take a look at that mind map and look at our ways of making an amine, so there it is. We could have an haloalkane, okay, to go into an amine. We can have a nitrile, or we can have a nitro. Okay, so technically haloalkane could work, okay, because we could add some bromine to that. However, it's a little bit difficult to control where that bromine gets added. So likely you will get the 2, 4, 6, in which case you might not get as much of this final product as you want. So that's probably not the best choice, just because you will get a lot of byproducts with that one. Okay, a lot more than what would be desired, because you would end up potentially getting this product, but still some bromine on there, right? So that's probably not the best choice. So the other choice, well, we didn't really talk about a nitrile group on that phenol, although it's potentially possible. We'd have to take a look at that. But one that would be really easy is having a nitro, okay? Because we did talk about using your dilute HNO3. Okay, and it would be actually quite important that you state dilute HNO3. Okay, and if we have dilute HNO3, or intermediate, benzene ring, that phenol will still be there. We could have the nitro being added to the 2 position. Okay, but to get this product, that's not the one we want. We want it added to the 4 position. So just like if we were to add a halogen to that phenol, we would have many products for that intermediate. It's the same. You would still have some nitro groups being added to that 2nd position, but you would have a lot higher of an atom economy doing it this way than you would with a halogen. Okay, so that would be our best intermediate. And then how do we go from a nitro to an amine? Just referring back, nitro to amine, we need concentrated HCl and we need tin. Okay, it does say reflux there as well, but the main thing they're going to be looking for is that it's concentrated HCl and tin. So on that dotted line, conc, HCl, and SN, tin. And that is that question done. Okay, so that's the end of that video. Nice and quick. If you have any other organic synthesis questions that you want help with, just leave a comment, send me a message. More than happy to do it. Next video coming up will be polymers. Okay, so remember, you are awesome and you totally got this.